All right, so I'm back at it. If you missed my stream earlier, I went over our first quiz, kind of covering functions. And what I want to do in this live stream is just kind of go over some piecewise functions. So that is something that we have begun in my class, talking about the piecewise functions. And I wasn't really planning on doing 2 different live streams in one day, so I didn't really have everything planned, prepared. So I'm sorry if the green screen is a little distracting for you. Obviously, in some of my other videos you see, that's the reason why I'm making some of these videos. So, or why I'm using the green screen. But for live streams, I'd like to change that. I'm just running out of time. And unfortunately, since I'm running out of time, I'm not going to have any time for kind of questions and answers. However, I will take a break during the homework as well as check the chat at the end. So if you do have any kind of questions or, if there's anything I can really, support or advice I can lend to you, I'll be happy to try to do that at the end as well as kind of a mid-break. So in this homework assignment, basically what I want to cover is graphing piecewise functions, evaluating those piecewise functions for different values, and then determining if the function is continuous or not, and if it's not continuous, being able to identify the discontinuities. So you can see here we have 4 kind of piecewise functions we are going to work on. And then we're going to work on finding the value k that makes the function continuous. And lastly, then we'll just kind of work on some multiple choice questions that will help prepare you for on that. So that is where we'll get to, or where we'll start. And I'll get going here in just a minute. So let's get up top and get started. All right, so in the first example, guys, when we're looking into graphing these piecewise functions, basically what we're doing is we're looking to graphing this function. So for instance, each of these equations, you can rewrite them, let's use red, as, y is equal to x squared minus 2. So let's just go and graph y equals x squared minus 2. So that is a parabola, right? And you're shifting it down 2. So it's going to look something like this. I'm not going to be exact with my graphing. All right, but I just want you to get the idea. However, then it says I only want this function to be defined for x values that are less than 0. So again, this is like your domain restriction. So this is what is restricting our domain. So we don't want our graph to include any values where the x is positive. So basically, we can just go ahead and delete the right side of the graph, and that's basically what we're completing here. Now, oops. Dang it. All right, I guess I'll have to do that again. The other thing that I was trying to do is you notice that this is x is less than. It's not equal to 0. So I'm going to create a hole there. And there we go. It looks something like that. Okay. The next one is the absolute value of negative x. So again, that is your V-shaped graph, right? And so the V-shaped graph, would look, again, you're just graphing, so that's the V-shaped graph, but you can see it's reflected about the x-axis is negative on the outside. But this says, so rather than graphing it in both directions, like the V-shaped graph reflect about the x-axis, we're only going to graph it for x values that are greater than or equal to 0. So in this case, we can eliminate all the negative portion of that graph. And then this is what our beautiful graph goes ahead and looks like. The next thing is let's evaluate for a -1, 0, and f of 1. So this one's really important because when we're looking at -1, we're looking for which function then is defined for negative values. And to understand the eliminating, you got to look at, well, this is function x squared minus 1 is the only function that's defined for -1. So it doesn't make sense for us to plug -1 into both of these functions. You can see the only point at -1 is the red graph, not the blue graph. So to evaluate for f of -1, all I'm going to do is plug -1 in for x of my top function, because that's the function that is defined for -1. So -1 squared is positive 1. 1 minus 2 is going to equal -1. Next one is to evaluate f of 0. And f of 0, you got to determine, well, which function is defined? Is it less than, or is it the greater than, or equal to? And since 0 is equal to for this function, we're just going to plug 0 in for there. So it'd be 0, absolute value. So the absolute value of 0 is 0. 0 times negative is still 0. So that value is 0. And again, you guys can see at 0 there's that point. And then we have f of 1. So at f of 1, again, this is for all values that are greater than 0, so we're going to plug it into that function. So we have negative absolute value of 1. Absolute value of 1 is 1. 1 times negative 1 is a negative 1. And you guys can see at 1, we're supposed to be at negative 1. Graph's a little off, but that's okay. Let's see the next question. Next question is determine if the function is continuous or not. This is discontinuous. Bad C. Oh, let's zoom in a little bit. So this function is discontinuous. And I'm going to say at x equals 0. And you can see here this is a jump discontinuity. At x equals 0 is a jump. And just remember, a jump discontinuity is non-removable. All right, so let's get into the next one. I did notice I made a mistake when I was plugging that in, so that's a negative. So we have two graphs that we need to discover here. And some of you might be more familiar with them than the other. So let's just go and kind of sketch the parent graphs here real quick. So again, the parent graph of 1 over x just looks something like this. And the parent graph of ln of x looks something like this. Okay? And so we'll talk a little bit more about when I get to those. Now the next thing is we've got to identify the transformations. So for this graph, we are shifting the graph 1 unit to the left. Okay? So I'm basically taking this graph and shifting it 1 unit to the left. Now the important thing here is for the reciprocal function is that we have a horizontal asymptote at 0 and at y equals 0 and a vertical asymptote at x equals 0. So not only are the hyperbolas getting shifted 1 unit to left, but our vertical asymptote is also going to be shifted 1 unit to left. It's really hard to draw straight lines, but I'm going to draw both these asymptotes here because that will help with our domain and range. Did I say domain and range? No, we don't have to do domain and range. Whew, thanks. Sweet. All right. But anyways here, let's go ahead and, so now I can just go ahead and graph this where it is. But again, this is actually, before I even graph to it, let's save some time. This is saying only graph values of this function for it's greater than 1. So if you notice here, the graph is on the left side of the asymptote and the right side of the asymptote. So technically I have a hyperbola here, a parabola there, and a parabola there. But it's only graphing for x values that are greater than 1, so therefore I can just not even worry about that one over there. The next one is kind of a little tricky as far as identifying the transformations. And if you remember in our transformations lesson, we talked about factoring out that b when you have a b and a c. So really, ln of negative 1 minus x can be rewritten as ln of negative x minus 1, which can be rewritten as negative x plus 1. So now what you see is we have a reflection about the y-axis. So this graph is being reflected about the y-axis, and it's going to be shifted 1 unit to the left. So if we took this function and we flipped it, and then we shifted it 1 unit to the left, I believe that would be the case right there. Flip it, and then if you took that graph, it's at 1, and then shifted it 1 unit to the left. Yeah, so it looks something like this. So let's do it a different color. Let's go back to blue. So my y equals ln of x would look something like that. Okay? So that is going to be ln of x. That is my reciprocal function. So I'll say ln of x, and just because I didn't clarify that, this is my 1 over x. All right? Now let's go and evaluate. So if I wanted to evaluate for f of negative 1, we got to determine, based on the domain restrictions, which function is defined for f of negative 1. Well, you can see that the ln of negative 1 minus x, that's the function that's defined for x values that are less than 1. So I'm going to plug negative 1 into this function. So I'm going to have ln of negative, now you could go ahead and plug it in right there if you wanted to. Let's use that version. Negative 1 plus 1. Well, negative 1 plus 1 is 0. 0 times a negative is 0. And therefore, the ln of 0 is just going to be equal 1. Okay, and I don't want to get back into logarithms and all that kind of stuff. That's not really the important of lesson. You could use a calculator for that, and obviously we wouldn't, we wouldn't be expressing that until we actually got to that unit. Let's go and look at f of 0. Well, as you can see, f of 0 is not defined for either of them. Wait, f of 0. No, I'm sorry about that. Oh, I wrote that down. That's supposed to be at negative 1. Oops, I messed these up. There we go. This is for x is less than -1. This is for, oh, man, I messed that all up. Duh. Okay, so I messed all that up because obviously the asymptote here is at -1. So I apologize for you guys. Let's go ahead and fix that. So at f of -1, so this is interesting. At f of -1, all right, the function, neither of these functions are defined. There's no place to plug in -1. You can see at -1, it's an asymptote. It's a vertical asymptote. So that is undefined. At f of 0, I guess I forgot my own homework question. At f of 0, you can see, well, which function is defined for 0? Well, this function is for all values that are greater than -1. So for all x values that are greater than -1, you use 1 over x plus 1. So that's where I'll plug in my 0. And you can see that gives you just 1 over 1, which is equal to 1. And then last but not least, I have f of 1. Well, that followed the same constraints there, so that'd be 1 over 1 plus 1, which is equal to 1/2. And you can see that this function is discontinuous. With a vertical asymptote at x equals -1. So remember, vertical asymptotes are infinite discontinuities, and they are non-removable. So I don't think I said that, but I just said, make sure you identify them and if it's continuous or not. You can also see the domain and range is all real numbers except for -1. This domain, or not, don't worry about the range for right now. The domain of this one right now is going to be all real numbers. All right, let's go and look at the cubic and the cube root function. So remember, guys, we just want to graph these equations. You're graphing this equation for less than 0, and you're graphing this equation for greater than or equal to 0. So kind of like interesting graphs here. If we look at the cube root graph, that's basically like the S curve. And then when you look at the, let's do it in a different color again. Now when you look at the cube root graph, that's kind of like another S curve, but it's like horizontally flipped, okay? So if I want to graph x cubed, but I'm only going to graph it for x values that are less than 0, let's do that game again. Why don't we do it like, oops. Why don't we graph it and then erase it? That's always fun. So, crosses at 0. And that's where it gets messed up. That's not a good S curve, but whatever. Either way, so that's a rough identity. It kind of like goes a little bit more horizontal here at the 0, but that's okay. But we're only going to graph this function for x values that are less than 0. So therefore, even though I graphed the whole function, we can erase everything to the right. And then now we want to graph the cube root function, which is the blue. And that function, we're only going to graph for x values that are greater than or equal to 0. Now, the important thing, too, which I kind of forgot to mention here, it's not equal to, right? There's a hole right there. So I'm going to have to mess that up, and that's all right. There's a hole, okay? But the important thing here is now when I do this cube root function, the cube root function fills in the hole. Right? However, this is only true for greater than or equal to, so therefore I'm going to delete where all the x values are negative, but that's what your graphing looks like. It looks really bad, but that's exactly what your graph is going to look like, or close what your graph will look like. All right, so now let's go ahead and evaluate. So if I evaluate for f of -1, evaluate for f of -1, that's -1 cubed, so -1 times itself 3 times, which equals -1. If I evaluate for f of 0, you can see here that, again, this is greater than or equal to 0, and this one's just less than 0. So therefore, I'm going to plug that into the cube root. So the cube root of 0 is just equal to 0. And then if I evaluate for f of 1, again, this is for all values that are greater than 0, so you're only going to plug it into this function. And again, you guys, you can look at the graph. Like at -1, I should have been down here to -1. At 0, I'm at, the function value is 0. Even though it's undefined for the other function, it's defined for the blue function, the cube root function, so therefore why we have a value. And therefore, f of 1 in this case is going to be the cube root of 1, which is just equal to 1. All right. Oh, and let's talk about this here real quick. So this graph is continuous. All right. All right, last graph here, we have the function 2 to the x, which is an exponential function. Remember, the exponential functions are going to have a y-intercept, when they're at least this form. They're going to have a y-intercept of 0, 1. All right, and we're just going to do a rough sketch. Now, this one says, though, x cannot equal 0. So at 1, where the normal y-intercept would be, there's going to be a hole. And also note there's a horizontal asymptote at y equals 0. But then it says, when x equals 0, we're going to have it equal 0. So again, the important thing here, the trick is, the exponential function has that y-intercept. In this format, it has a y-intercept of 0, 1. All right? And basically, that's it. So let's look at the evaluating this good old monster. So we have f of negative 1. Well, guys, this is true for all values, just except for when x cannot equal 0. So f of negative 1 is going to be 2 to the negative first power, which is equal to 1/2. F of 0, we can't plug 0 into this equation because it says this equation is only true for when x cannot equal 0. So we're like, hey, well, what is about f of 0 then? Well, it's equal to 0. Okay. And again, guys, remember, if you were able to plug it, 2 to the 0 power is 1, right? Okay. I think I mentioned that, but whatever. And then f of 1 here is going to be just plugged in, so that's going to be 2 to the 1 equals 2. Sweet. All right, the next one is find the value k that makes the function continuous. So the way that I kind of like described this with my class earlier today was, looking at this, if you have like a function and like, here's your one function and then here's the other function. Like what value, okay, like so let's say this is, f of x plus 2. And then this one is, let's not call it f of x, let's call it something else. Let's call it like g of x or something. G of x plus k. And if I said, all right, how high do I need to move k so that it covers up with f and that they're going to be the same? And you could say, well, if k was equal to 2, then these two functions would now be continuous, right? And that's basically what we're looking at. We're looking at what do I need to do to move g of x, sorry, not k, g of x up so that it's the same function. And what's really important is when you have them now continuous, the x and the y coordinates, they share a common point. They share an x coordinate and they share a y coordinate, all right? And what we have learned in this last lesson is when these functions are discontinuous, the first example, second example, and fourth example, they're all discontinuous. They're all discontinuous at their domain restrictions. The domain restrictions are, changing at 0. That's where the discontinuity is. The domain restrictions are changing at negative 1. That's where the discontinuity is. The change restrictions are at 0. That's where the discontinuity is. And again, what we're looking into doing is how can we take the discontinuities and marry them so there are none. So the important thing is if these functions are going to be connected, they're going to be continuous. That means they need to be continuous when x is equal to 1 because that's where the graph is like going to break apart into two different ways. So we know that they need to be the same. So basically y, like here is 1y, like y equals, I'll just use that. So y equals and y equals. So when x equals 1, these two equations basically need to be the same. We basically have to have y equal to the y. And that's going to be at x equals 1. So we want the y coordinates of the points to be the same when x is equal to 1. So the really simple thing, guys, is rather than saying the y, we can say, well, this y is equal to 2x plus 3, and this y is equal to kx minus 3. So we just set an equation, say 2x plus 3 has to equal kx minus 3. The y coordinates have to be the same. And then if we want to find out which coordinate, they need to be the same when x is equal to 1. So now we just plug in a 1 in for x. So that is at x equals 1. So now we just got to solve for k, and that's going to be the value that makes the function continuous. So we just get this. This is going to be 2 plus 3 is 5 equals k minus 3 plus 3 plus 3. K is equal to 8. Bam. Now, I'm not going to go through this, but if you wanted to graph 2x plus 3 as well as graph 8x minus 3, you would see that the graphs are going to intersect at exactly those, are going to intersect when x is equal to 1. So therefore, you can see how k is going to be the value. Now, on the next one, you can see we have a rational expression. And so rational expressions are kind of interesting because we know that x cannot equal negative 1 because, again, that's going to make the denominator equal to 0. But we want to make sure we understand, well, can it not equal negative 1 because there's a vertical asymptote going on there? Well, no. It can't. It's not a vertical asymptote because they're giving us a value of negative 1, which is k. So what that tells us is x plus 1 is a whole, meaning it's removable. So if I remove that discontinuity, I can evaluate for the function at the missing whole, right? It's kind of like this. Like if I want to figure out what is the value of 2 to the x, well, you got to find the value of the whole, right? So they're saying, oh, at the whole it's equal to 0. Okay, but it's saying x cannot equal 0. Well, you got to find the whole and plug it in. And if you plugged 0 into 2 raised to the x, you would get 1. And that's the value that plugs in the whole. In this case, we can't plug in negative 1 because it's actually it makes the denominator equal to 0. So what I'm going to do in this case is simplify my rational expression. I'm going to factor this to x minus 3 times x plus 1 all over x plus 1, where x cannot equal negative 1. And I have k, where x is equal to negative 1. And now what you can see is my x plus 1s divide out. So now when I rewrite this, I now have x minus 3 when x is equal to negative 1, and then I have k when and I have k is when x is equal to negative 1. Well, guys, now I can plug in negative 1 into this equation. So I know I'm kind of running out of space here, but if I plug in negative 1 minus 3, I get negative 4. Okay? And so that is going to be my k is equal. So k is equal to negative 4 in this case. And if you were to graph this equation, all right, if you were to graph this equation, x squared minus 2x minus 3 divided by x plus 4, what you'd see is you'd see a line. And your graphing calculator is not going to show you a whole. But if you look at the value at negative 1 of that equation, you're going to get negative 4. And that's the value that's going to plug in that hole. So, all right, guys, I have some multiple choice here. I'm just going to take a quick little break. Just kind of check in, see that I have some people have joined in. And people joined in, so I'm just going to take a quick little break. You might be taking a video out of it. Let's see. Answer my question. I was gone for like 10 minutes. I'm not sure what your question was. How do you graph a circle 3x squared plus 3y squared equals 12? So the first question here in the live stream, I'm kind of a little short on time, but I can tell you basically you need to identify the center, which in that case is going to be your h and k, which in your case is 0, 0. And then you basically just take once you find the 0, sorry about that. You want to make sure you first have this in standard form. So we don't want to have any coefficients with our x and our y, so you'd want to divide by 3 on both sides. So therefore you'd have x plus y equals 4. Then, now you can identify the center, which is your hk, which in your case is 0, 0, and then equal to your radius, which remember it's x squared plus y squared equals r squared. So therefore you need to take the square root of what your equation is equal to find your r. That's a very quick and rough determination. I have a ton of examples on circles with that. If you just go ahead and search my channel. So Savage Lou says, how's life? I'm not ignoring you. I'm just trying to get this live stream finished up here so I can finish through here. My salary is my public school salary based on there. Nope, I'll come back. So seems like he is teaching himself because no one's watching. Well, yes, you're right, Raul. That's part of it, but that's okay, man. Hi, Dimitris Pota. Hey, man. Well, happy to have you join on the live stream. I got my math degree from Western Michigan University. But I do teach now down in Florida. All right, guys. Well, thanks for joining. I'm going to just finish off these multiple choice questions now, and so I can wrap up and head home. So, and this one is saying find the y-intercept of f of x. So we have two equations, right? And we got to think here. Like the functions are separated at 2, right? Where this function is for all values that are greater than 2, and this function is solved graders that are less than 2. Well, I don't really care to find anything that's greater than 2, so I'm not going to be worried about that one. I want to find the y-intercept of x squared minus 4. And remember, guys, we can just write that as an equation, y equals x squared minus 4. Right? So to find the y-intercept, so the y-intercept is when x is equal to 0. So I just say y equals 0 squared minus 4. Y equals negative 4. And we could write that as a coordinate point of 0, comma, negative 4. Answer is B. The next one, find h of negative 1 for ... So again, what we want to do is identify, well, where is negative 1? And you guys can kind of look at this like, you know, this function is for all values that are less than negative 2. Okay, I'm not looking for negative 1. This function, this domain is for all numbers between all values between negative 2 and 3. Well, x equals negative 1 is contained in that, right? So therefore, that's the function I'm going to want to use. Then I need to plug in h of negative 1. So h of negative 1 is equal to negative 1 cubed. So negative 1 cubed, I think we already did a problem like that, is going to be negative 1. So that's going to be C. And then the last one we have here is f of negative 4. So again, we're looking for, you know, what are the domain restrictions that are for negative 4. Well, this one's saying x is less than or equal to negative 1. This is saying for all values that are greater than negative 1. Negative 4 is less than negative 1, so you're going to want to plug that into the second equation. So f of negative 4 is equal to 6 times negative 4. 6 times negative 4 is a negative 24. And there you go. So, all right, guys, that is kind of it. Just in enough time for me to wrap everything up. I do have some questions coming in here and put it up there. Jeez, oh man, you guys get out of control. All right. So, this stream, to answer your question, this stream will be up, so you guys can, you know, go back to it or use it however you want to. All right, guys, you guys can go ahead and have fun. I am going to wrap this up. I hope I was able to help you guys out with you know, piecewise functions, and I also did an earlier stream on a quiz for function transformation. So if you enjoyed that, really I appreciate the opportunity to be able to help you guys out, and I will look forward to going live next week. I'm not sure what days I'll be going. Probably, you know, you can probably look into me going live on Tuesday, Wednesdays, or Thursdays, and I'm probably going to be staying around the 3, 4 o'clock, you know, kind of time frame. So that's what I have coming up for next week, and then I'll just check in with you guys till then. So cheers, guys. Hope you enjoy the rest of your day, night, morning, anything else.